Section 9.4a is on solving exponential and log equations. So that's what we're going to be focusing on in this video. I'm going to skip the review questions just for this video, post those on the notes. Solving exponential equations. We're going to have a few different situations that you're going to look at. The first one is if you have two powers with the same base, so their bases are equal, then their exponents must be equal as well. And really that's intuitive, it should make sense. If you have 2 to the x power equals 2 to the third, then x must equal 3. Because 2 to the third equals 2 to the third. So if the bases are the same, then the exponents must also be equal. Makes sense. Of course, it's going to get a little bit more complicated, but that is just the basic rule there. Now these ones, evaluating a logarithmic expression, in your calculator you can type in log base 10. But any other log, unless it's an advanced calculator, you have to either use the change of base formula or rewrite it as an exponential and log both sides. So one way of doing this, evaluating it, if you think about it, and let's just say that the log base 3 of 8 equals x. One way of doing it is to rewrite it in exponential form. So 3 to the x power equals 8. Then we can, because exponential and logs are inverse functions, since I have an exponential function, if I take the log of both sides, then I can finish solving it. The log base 3 of x, this x comes out front, that's the rule, so it's x times log base 3, or log of 3, equals log of 8. And I just did the common log, so this is common log base 10. And then to finish solving for x, then I say divide by the log of 3 on both sides. And x is going to equal log base 8 of log base 10, common log of 8 divided by log of 3. So log of 8 divided by log of 3. And I could use a calculator to approximate that. Let's see if I still have that calculator open here. So I got log of 8 divided by log of 3. It's approximately equal to 1.8927. So 1.89 approximately. So log base 8 divided by log base 3. Just make sure I type that in correctly. So the rule that I used there was if you have the log of, let's just say this is log of y to the x power, you can rewrite that as x times log of y. So that's just a common rule. You can take that exponent and take it out front. So that's log both sides. That's the way to undo an exponential. There is something called change of base formula. And it works really nicely if you can remember the formula. So if you have log base b of x, then the change of base says that that's the same thing as the log of x over the log of b. So you go from a log base b and you change it to common log. So just log of x over log of b. So I always remember it because the x is on, the big one goes on top, and then the log of b goes on the bottom. So log base 4 of 15 would be the same thing as if you did log of 15 over log of 4. And it's called change of base because I'm changing it from base 4 to base 10. And I want to change it to base 10 because now I can evaluate that with the calculator. So then I can use the common log button in the calculator to say, how do I remember how I clear this? Oops, that's not what I wanted to do. Clear. Okay. Log base 15 divided by, what was it? Log base 15 divided by log of 4. So I changed it from a log base 4 to log base 10 because in your calculator then you can do log base 10 and you can get an approximate answer of 1.95. It continues infinitely, but 1.95 is my approximate answer. So change your base or log both sides, either one. This is using the idea if the bases are the same. So 2 is the same base, and if the bases are the same, then the exponents must also be the same. So to solve for x, I can set the exponents equal and then solve by getting my variables on one side and my numbers, constants on the other, and then isolating the x using inverse operations, and I get x equals 1. And if you plug that back in, then 6 times 1 is going to be 2 to the 6th. 3 times 1 is 3, plus 3, you're going to get 2 to the 6th. So x equals 1 does work there. So if the bases are the same, then the exponents must be the same as well. So same idea, if the bases are the same, then the exponents are the same. So if they both have a base 10, then you can set the exponents equal and solve for x. Get the variables all on one side and get the constants on the other. So you're going to have 4 equals 2x, then use inverse operations to get x by itself. So x equals 2. Notice this one, number 2 here, this is the same type of problem, but it looks a little different. I have 4 to some power equals 16. But you have to use your critical thinking and say, okay, 16, that's the same thing as 4 squared. Well, if 4 squared equals 4 to the x plus 1, now my bases are the same, which means my exponents, 2 has to equal x plus 1. Finish solving for x, and we get x equals 1. So x equals 1, because 4 squared here would give me 16. So that's a little mental math too, but since if the bases are the same, what's raised to the power has to be the same. It works similarly with logs. If you have the same log on both sides of an equation, then what's inside the log has to be equal. So for example, this one, I have a natural log of 2x plus 3 equals a natural log of 5x minus 6. Since they're both natural logs, because the natural log of 3 has to equal the natural log of 3, for example, if these are both the same, then these have to be the same as well, which means I can set 2x plus 3 equal to 5x minus 6 and then solve that for x. So 2x plus 3 equals 5x minus 6. And then just solve. So I'm going to start by subtracting 2x. And on this side, I get 3 equals 3x minus 6. Since I moved the x's to the right, I'm going to move the constants to the left. So 9 equals 3x. 3 times x, so inverse operations of dividing, I get x equals 3. Here I have log base 10, so log of x plus 3 equals log of 3x plus 1. So that means that x plus 3 has to equal 3x plus 1. Finish solving for x. So subtract an x on both sides, 2x plus 1, 2 equals 2x, divide by 2, x would have to equal 1. What you do have to remember is that exponential functions and logs are inverses of each other. So a couple things, if you have log of b to the x, that's the same thing as x times log of b. Kind of what I was telling you before. So you can take that exponent and put it out front. That's one of the rules for logs. Also, if you have log base b of b to the x, well, anytime that the base is the same thing as the number that you're evaluating the log of, they kind of undo themselves. So in the first example, this was log base 10, you bring the exponent out front. If the base is the b in this number is the same, then it equals the exponent. So taking the log of both sides. So log and log of 8. So logging both sides, because then I can take this exponent of x and take it out front. So it's the same thing. Log of 5x is the same thing as x times the log of 5. And that equals the log of 8. Then I can solve for x by dividing both sides by the log of 5. So x equals the log of 8 divided by the log of 5. And then you can use a calculator. Log of 8 divided by log of 5. So log of 8 divided by log of 5 equals approximately 1.29. So approximately 1.29. You could have also went back to exponential form. Remember, that would have been log of base 5 of 8 equals x. You could rewrite 5 to the x equals 8, rewrite it in log form, and then use the change of base formula, which is log of 8 then divided by log of 5. So changing it back to that common log so that you can evaluate it for a number, like 1.29, it's approximation. For anything with an e, you have to remember that ln is base e. ln of x is the same thing as log base e, so, or ln base e of x. So if you're given an e to some power, when you take the log of both sides, you need to use the natural log. So you need to do the natural log of e to the negative x equals the natural log of 5. And then you bring this exponent out front using that property of logs. So it'd be negative x times the ln of e equals the ln of 5. Now, because the ln of e, ln is base e of e, that's going to equal 1, because remember, e to the first equals e. So this right here equals 1, so you're just left with negative x equals the ln of 5. So we can divide by negative 1, so x equals negative ln of 5, the negative natural log of 5. In a calculator, if we wanted the approximate value, you would do negative, trying to get used to this calculator here. Is it negative ln of 5, which is approximately negative 1.61. Negative 1.61.
Excuse me. All after-school activities have been canceled for tonight.
Oh, storm.
Again, all after-school activities have been canceled for tonight.
So taking the log of each side, continuing with examples like that. Before you do that, just like if you're going to solve 2x plus 1 equals 7, before you divide by 2, you need to subtract 1 on both sides. So you get the variable isolated before you do anything with it. It works the same thing with exponential and log equations. You want to first start by, adding 6 to both sides. So then we get 10 to the 2x equals 1, be 152. And then I can take the log of both sides. So I'm going to use log base 10. This exponent comes out front. That's the rule with exponents. So 2x times log base 10 equals log of 152. Now log of 10 really is log base 10 of 10, which always equals 1, since 10 to the first power equals 10. So right here equals 1, so that is kind of gone. I'm going to finish solving over here. So I get 2x equals log of 152, and then divide by 2 on both sides, and get x equals the log of 152 divided by 2. I can't simplify the 152 with the 2 because it's log of 152, not 152 by itself. Approximately, I'd have to use a calculator to find the approximate value of that. So log of 152, close the parenthesis, divided by 2 is approximately equal to, 52 divided by 2 is approximately equal to 1.09. So 1.09. typically I'm going to ask for the exact answers. So we're going to leave it as log of 152 over 2. Starting here, I'm going to subtract 9. I'm going to isolate that variable. Negative 4 e to the x equals negative 4. Divide by negative 4 on both sides. Get e to the x equals 1. Then remember that ln goes with e, so I'm actually need the natural log of both sides here. And then the exponent comes out front, so we get x times the natural log of e equals the natural log of 1. Then the natural log of e always equals 1 because it's ln base e, and e to the first equals e. So anytime the bases are the same as what you're evaluating, it equals 1. So a natural log of e is 1, so you get x equals the natural log of 1 as an answer. The natural log of 1, using my calculator again, you use ln of 1 is approximately, or not, it's equal to 0. Oh yeah, we knew that too. And so that equals 0. So 0 is my answer. Because anything to the 0 power is 1. So if you have ln of 1, e to the 0 equals 1. So it equals 0. Then you can also exponentiate each side. So that's the reverse. If you have 5 to the x equals 25, you can log both sides. Even though you know the answer here is 2, you could do log of both sides. So it'd be x log of 5 equals log of 25. And divide by the log of 5 on both sides. And you're going to get x equals 2 if you plug that in your calculator. So if you start with an exponential equation, take the log of both sides. If you start with a log, exponentiate each side. So since I have log base 5, I'm going to use this as the 5th base. So I'm going to take this 5th to this power and 5 to this power. So do it on both sides. Now log base 5 to the log base 5 is going to cancel, and I'm just going to get x plus 2 equals 5 to the 6th power. You know, I should have figured that out, but I don't know what 5 to the 6th power is right offhand. So 5 to the 6th power, 15,625. So x plus 2 equals 15,625. Finish solving for x by subtracting 2 on both sides. So x equals 15,623. So taking the base and using it as a base in an exponential equation. So if I have this one, I'm going to slide it over here a little bit. ln of 2x equals 5. You have to remember that the ln is base e. So I'm going to take e to this power and e to the power of 5. So doing it on both sides. Now e to the ln will cancel out the ln and just leave what's left. There's 2x, so just this is left. And e to the 5th is irrational, so it's kind of like pi times 5. It's a decimal, but it's e to the 5th power. So that's 2.71 to the 5th power. So I can just leave it as e to the 5th, divide that by 2, and we get x equals e to the 5th divided by 2. Whoops. E to the 5th divided by 2. I can approximate that using a calculator, and I could say that, if I can get back to my calculator, I could say that e to the 5th power divided by, so e to the 5th power, divide that by 2, and I could say that that's approximately 74.21. So 74.21. But this is the answer I want, the exact answer there. Okay, lots to learn, but this is what you have to pay attention to. Make sure to check for extraneous solutions. Remember, those are answers that look like they work, but then they don't. So, you know, I don't think we had any in this case, but I'll have to go back and look. All right.